similar characteristic to those of JFET, and additional characteristic is very useful in MOSFET. So due to the structural change, whatever advantages we have, that is useful. MOSFET are of two type. One is depletion type MOSFET, another one is enhancement type MOSFET. This depletion type MOSFET is also known as DMOS. If it is silent, actually this is D MOSFET and E MOSFET. Okay, so one by one we'll discuss. Now, first we'll understand the depletion type MOSFET. So how we'll construct the depletion type MOSFET? First, we have to take one semiconductor. Let us take one semiconductor. Let us take P-type semiconductor here. Okay, so this is called a substrate upon which the semiconductor component will be built. Once you take the P-type semiconductor, then two wells will be created here with opposite type of semiconductor. So these two wells will be of N-type. Okay. Now, above which we'll take one insulator or oxide layer. So this is my oxide layer. Okay, this is semiconductor. This is oxide, upon which, as in JFET, we have three terminals: gate, source, drain. Here also three terminals are there. So how we'll take the contact or the terminal source, gate, drain? We'll take the terminals here. This is one terminal. This is another terminal. This is another terminal. So this terminal is called as source. This is drain as D. This is gate. Okay, so I've got three terminals here, and between source and drain there will be a channel or same type of material which we have taken as source and drain. Okay, this is also N-type material. So this is channel. Okay. Now, if you observe here, this is my metal contact from which we will take source, gate and drain terminal, and the name of the component or structure is given due to this. If you observe from top to bottom, how we'll move? First we'll see metal, then oxide, then semiconductor. That's why the name is given as MOS. And the working principle as field effect transistor, we'll see how the voltage, input voltage change will affect output current. So that's why the name is given as MOSFET. Is it clear? Guys, is it clear? Any doubt?
Yes, sir.
Now, this is depletion type MOSFET, and the channel is N type. So that's why this is called as N channel D MOSFET. Okay, this channel is between source and drain. N channel is there or N type material is there which is connecting. So that's why it is called as N channel depletion type MOSFET. So whatever I have explained, that is written here: drain, source, gate, and this oxide is generally silicon dioxide. So that is SiO2, which is oxide or insulator. And the bottom one, the substrate, is also one terminal that is called as body or substrate. Okay, generally represented as SS. So in fact, this is 4-terminal device, but source and substrate are sorted. So you can also take 3-terminal device. For you, it is sufficient to know 3-terminal device. 4-terminal device means you have to apply some other voltage to substrate, which is not used for you. Now we'll understand here how you can control the output current using this input voltage or the operation of FET. Okay, like JFET we have discussed, the input voltage gate to source voltage is changed, then output current, drain current is changing because the reverse bias junction across the channel is more reverse bias or the depletion region increasing, decreasing due to the channel width decreasing. So current is decreasing. Here also we'll observe the output current, that is drain current, is affected by gate to source voltage. Then you can say this is operating as a field effect transistor. See here. Now, if I take the semiconductor, this component, like this. Okay, so this is P, this is N, this is N. Now, this is also N-type material. So I'll find electrons here. Here also I'll find electrons. Here also I'll find electrons. What is my objective? Like in transistor or BJT, what is my objective? I want to transfer the carriers from emitter to collector, and through base I'm controlling how much charge is transferring from emitter to collector. Similarly, JFET, I want to transfer the carriers from source to drain, and through gate to source voltage or through the gate terminal, I'm controlling that how much current or how much carriers are moving from source to drain. So this controlling of output current or how much current, how many carriers are moving from source to drain is important. Here also same thing will do. My prime aim is to transfer the carriers from source to drain, and using the gate terminal I want to control that current. Now here, if I apply without applying any voltage to drain or source or gate, can I get any current? Can the electrons move and produce any current? Obviously no, because you have already seen at any temperature, or we can say the room temperature, the electrons having thermal energy and they move randomly inside the material. So the random motion or net motion of all these electrons will be zero. They'll produce no current. So if I'll not apply any voltage, electrons will not move unidirectional and current will be not produced. So for that we have to apply some voltage. Okay. So if I apply voltage to the drain terminal, that is positive voltage, then only the electrons will move from source to drain. So this is my electron movement. If electrons are moving from source to drain, then obviously the current will move from drain to source. Then I can get the current. Now this current will be controlled by the voltage between gate to source, right? So how I'll control that one? if I apply, let us say, negative voltage, okay, I'll negative voltage apply. So here this will be negative. Now when I give negative voltage to the gate terminal, what will happen? This negative potential at the gate will repel the electrons. So the electrons will be repelled from the channel, as well as the holes which are present in the p-type material as majority carrier, they will be attracted towards the channel, right? Now what happens across the channel? If you observe this channel region, what will happen? The number of electrons will decrease because they are repelling through the negative potential, as well as the holes are attracting or moving to the channel region. So they will recombine with the electron to produce neutral. Okay, electron and holes will recombine, then they will neutral. So if you observe this one, it is inclined. You see the vertically, if you take, then you can understand. See, this is my gate terminal. I have applied negative voltage here. So this negative potential is repelling the electrons. You see the electrons arrow mark are outside the channel, as well as the holes are moving into the channel. So in the due process, they will get neutralized, so that the electrons concentration will reduce in the channel region. Electron concentration reduces means the number of electrons which are crossing from source to drain, that will also reduce. That means what happened to the current? Can you tell me? If number of electrons are less in the channel, ID will increase or decrease?
Decrease.
Increase or decrease? The number of electrons decreasing means current will decrease or increase?
Decrease.
Decrease. So current will decrease. Now if I increase more reverse bias, then more decrement in the current. So in that way, if I apply negative voltage here or the potential across gate to source terminal, then I can control the output current, which is ID. Okay, so that is same as the operation what we have discussed in JFET. By controlling the gate to source voltage, the current will be controlled, right? So that's why it is FET operation. Now we'll start our discussion with minimum reverse bias, or the less voltage or less negative voltage, then we'll increase, then we'll see how the current will produce and what is the characteristic of the graph. Now so yeah, okay. Now see, what is the minimum voltage of negative? 0 or not? Minimum value of negative means less negative. What is the minimum value? 0, right? Then we'll increase that one, more negative, more negative. So first I'll do, you see this figure, this is also written here. So I'll sort it here. So VGS 0 volt, and the substrate, this is my substrate, I'll sort it here also. Okay, so gate to source voltage is 0, and just a minute. Okay, so gate to source voltage is 0. Then I'll connect VDS, then to source voltage here. So this is your VDS, right? Now tell me, if I connect, already I told you when I give VDS 0, then current is not flowing, right? Now when I increase the VDS from 0 to 0.5, 1 volt, 2 volt, then what will happen? This positive potential is increasing here, right? This positive potential will increase means more and more electrons will be attracted from source to drain due to positive potential at drain terminal. Then current will increase or decrease. If I'll increase the VDS, the current will increase or decrease? ज्यादा पोटेंशियल, ज्यादा पॉजिटिव वोल्टेज यहाँ पे ड्रेन पे दूंगा तो इलेक्ट्रॉन नंबर विल इंक्रीज एंड current will increase. So if I plot the graph between VDS versus ID, then when VDS 0, current is 0. Now I am increasing the VDS, then current will increase linearly. Okay? Yes or no? Now this is happening. Now tell me, are you able to see any PN junction here? This is P, this is N, this is P, this is N, this is P, this is N. So across source to channel to drain, I am seeing the PN junction here, and this PN junction is forward bias or reverse bias. This is connected to positive, that means N type is connected to positive, and P side is connected to ground. This is like a diode where P and this is N, P is connected to 0 and N is connected to, let us take here 5 volt. This is 5 volt. So this junction is forward bias or reverse bias? Reverse bias. So there must be some depletion region here. Okay. So I am drawing the depletion region here. So this is your depletion region. Now, like in JFET, I have explained drain side will be more reverse biased compared to source side. Here also same thing. I am giving here 5 volt between these two terminal. So drain is connected to 5, source is connected to 0. So compared to drain, source side will be less reverse biased. So the tapering of the depletion region will arise like JFET, more wider depletion region across the drain side and less in the source side. Now, again I'll increase the reverse bias, more increase in the voltage across the drain. Then what will happen? The depletion region will increase or not? This is PN junction diode. If I connect negative voltage and I'll increase, then initial depletion region is like this, means the incremental voltage when I apply, the depletion region will increase. So this depletion region is penetrate in the P side as well as N side. Yes or no? When depletion region increases, it will penetrate to N side as well as P side. So here also, when I increase the VDS, the depletion region will increase. That means the depletion region will penetrate to the P side as well as the upper side. When it will penetrate to upper side, क्या हो रहा है? फिर से चला गया तो okay. Now depletion region will penetrate this side as well as upper side. So when penetration in upper side, then it will move like this. Okay. Still increase in voltage, it will more penetrate into the channel region. So what you are observing, the channel's width. Earlier the channel width is from here to here. Now it is decreasing from here to here. So a time will come when I increase the VDS, it will fully block the channel. That means whatever the electrons are moving from source to drain, now they can not move to the drain side. Now when the electrons will not reach to the drain side, then current will reduce to zero. Yes or no? अरे हाँ कि नहीं? अगर इलेक्ट्रॉन सोर्स से ड्रेन तक नहीं पहुंचेगा तो करंट विल रिड्यूस टू जीरो और नॉट?
Yes, sir.
Current will reduce to zero. But as in case of JFET we have seen, practically observation is that there is still increase, means a narrow channel is existing between this source and drain where the constant current will flow. That means as initially when I increase the VDS, current increases, that will not happen, but whatever constant current is going, that will maintain there. So when I increase the voltage, initially from zero the current is increases, but after certain voltage the current will stop increasing. So after this point, let us take current is saturating. So VGS, what I have taken this one, VGS 0 volt. Okay. And as in case of JFET also, here we can say this is my pinch off voltage. The voltage at which channel blocks and current saturates, that is pinch off voltage. And this current is IDSS. Okay. So same characteristic we have seen in the JFET, here also same characteristic we'll see. Now we'll go for negative voltage. Now instead of this 0 volt, I'll give some positive voltage here. Sorry, negative voltage I'll apply. Negative voltage, so plus minus here. So let us take minus 1 volt. If I apply negative voltage here, then negative potential I'll see. So these will repel the electrons and attract the holes. Holes will be attracted, electrons will repel. Then what happened to the channel strength? The electrons across the channel will reduce or increase or remain constant when I apply negative or minus 1 volt. Tell me. Compared to when I have connected 0 volt, when I apply minus 1 volt, the channel electrons will reduce or increase or remain constant. तो क्या होगा बोलो? Negative potential will repel the electrons towards the substrate. It will attract more holes, so recombination will happen. So electron strength will reduce or increase or remain constant in the channel. No one is replying. Already I have explained one time. This is the second time I am telling. Huh? Respond. I'm asking something. You should unmute and tell.
Sir, I think it will be reduced.
It will obviously reduce because the electrons are repelling from the channel, means
Yes, sir.
the number of electrons will reduce in the channel. So number of electrons are reducing means the current will also reduce. Yes or no? So
Yes,
compared
sir.
to the case 1, when 0 volt is connected or get to source is 0, how much current I'll get? When I connect -1, obviously less current I'll get. Keeping all the condition remain same, like when I start VDS from 0 to positive voltage, current initially will increase, then saturation happens. Okay, so everything remain same. So you see here, this is the first one what I have drawn. VGS 0 volt. When I increase the VDS, then current will increase. Then at this point saturation happens, then current saturate. Now I am giving -1 volt. Okay, so the junction is more reverse biased and the channel strength, the electrons in the channel region is reduced. So the current is reducing here. So pinch off occurs little bit less and it will saturate here. Similarly, -2, -3, -4, -5, and finally at -6, when I apply -6 volt, then the channel will be not available. That means no carrier will be available across the channel, so current will not flow. That is your VGS off or V pinch off. Okay. Now this is the case when I connect negative voltage. Now when I connect positive voltage, tell me what will happen. Suppose I'll connect here positive voltage. Plus 1 volt. So this is plus, this is plus, this is plus, this is plus. Okay. So when I apply positive voltage across the channel, what will happen? This positive potential, you see, one thing is very evident here. If you observe the structure from here to here, this is like a parallel plate capacitor. Okay, so what is the role of capacitor? How we take two conducting plate. Okay, this is one conducting plate, bottom one is another conducting plate, and between that insulator is there. Okay, so whatever positive voltage you are giving, negative potential will be appear here. Is like capacitor. So same thing is happening here. So this plate is metal and the bottom plate is semiconductor, both are conductor, and in between that oxide is there which is insulator. So it will act like capacitor, parallel plate capacitor. Okay, so when I apply positive voltage across the gate, the electrons which are present in the p substrate, already electrons are available. Okay, already electrons are available. Now due to the positive potential, it will attract more electrons. from the P substrate. Now in the channel, the number of carriers are increasing or decreasing due to positive voltage at gate. So when more electrons are coming from substrate to the channel strength or electrons will increase or decrease.
What you have asked, sir? One more time. Can you repeat it?
When electrons are attracted from the substrate to the channel by applying positive voltage at the gate, the number of electrons in the channel will increase or decrease?
Increase, increase.
Increase. Then what about current?
Sir, it will also increase.
It will also increase.
Yes, sir.
Keeping all other conditions constant, the reverse bias junction, when I increase VDS, the depletion region will penetrate to channel, everything remain constant, will get more current compared to 0 volt. Okay, so the graph will shift upward like this. This is VGS plus 1 volt, and when I apply negative voltage, this will be minus volt. Okay, current will decrease. So that is shown here. When I apply negative voltage, current is decreasing because channel, the number of electrons in the channel is reducing. When I apply positive voltage, the number of electrons in the channel will increase. So I am getting more current. Okay. So this decreasing trend in current is called as depletion mode. Okay, and increasing trend is called as enhancement mode. The name of the MOSFET is depletion type MOSFET. Depletion means generally we say decreasing trend or decreasing or void or less, like that, because depletion region we are defining what? The region where we are not finding any mobile charge carrier, or the region depleted of mobile charge carriers are called as depletion region in the PN junction. So depletion means it is decreasing or less, or you can say the void of carriers we assume, or decreasing trend we can assume. So though the name is depletion type MOSFET, we can increase the drain current as well as decrease the current. So for increasing current, we say enhancement mode operation, and decreasing, we are saying depletion mode operation. Okay. The same thing if you want to plot as transfer characteristic, like input voltage versus output current, then see here, this is your output characteristic, output voltage versus output current, where you have discussed VGS off, then V pinch up, this is your VP, V pinch up, and for increasing it is enhancement mode, for decreasing it is depletion mode. Now when I plot the input voltage versus output current, then I have to take x-axis as VGS and y-axis as ID. How will plot? You see, whenever I have taken VGS 0 volt, what is my current? That is IDSS, this point. So I'll take VGS 0 and extend this line here. So around 8 milliampere I am getting as IDSS. Now for VGS minus 1, again I'll extend this one, and this is my minus 1 line. So this is your minus 1 current. For VGS minus 1, I'm getting that much of current, maybe 5 or 5.5 milliampere current. Similarly, for minus 2, so this is my minus 2 line. So here I am getting current as around less than 4 milliampere. Similarly, for -3, this is -3, then this is -2. Oh, sorry, -3, -4. Okay, then -5 up to this point, small current. Then at -6, I'm getting no current. So this is your -6. So if you join all these points, then we'll get depletion mode characteristic. Similarly, if you take VGS positive, then you have to extend here. So around 10.9 it is given here. This is for hypothetical situation. Okay, depend upon the type, you can increase or decrease. So you'll join here, then you'll get enhancement mode operation. So basically from this point, VGS 0 point, the current is increasing here and it is decreasing here. So decreasing trend means depletion type and increasing means enhancement mode is called. Okay, but the name of the characteristic or the name of the transistor is depletion type, but we can operate that one as enhancement as well as depletion mode. Clear? Now see here. So if I take the equation like current equation in JFET, that is also valid in MOSFET. So ID equals to IDSS 1 minus VGS by VP whole square. It is also valid in depletion type MOSFET. Because when you take VGS 0, I'll get IDSS. Okay, this is your IDSS. Let me zoom a little bit. See, when I take VGS 0, I'll get 0 by something, that is 0, 1 minus 0, 1 into IDSS, that is IDSS, what I have marked here. And when VGS less than 0, ID less than IDSS. So less than 0 means this is negative trend. So that is coming as less than IDSS. IDSS by 2, IDSS by 4 or less than that. Okay. So that equation is valid for this one also. Similarly, if you take increasing trend also, it is validating. So when VGS is positive, like +1, then ID will be greater than IDSS. Okay. So IDSS this point. So this is your more than IDSS. That is also valid. Now VGS is positive. So though the name is depletion type MOSFET, we can operate as depletion mode or enhancement mode, and current equation is same as JFET current equation. And if you take P-type channel or P-channel D MOSFET, same thing, operation remains same, only the voltage polarity will be changed. You see here, in that case, we have taken VGS negative voltage, then the current is decreasing. Now here, VGS positive voltage, current is decreasing, and pinch off voltage is also positive. And when I apply negative voltage, then current is increasing. And if you observe the transfer characteristic, then obviously this will be right side because VGS is positive. So at this point, this is my 0 point or VGS 0. I'm getting this much of current, which is IDSS, and VGS positive means we are decreasing the current, or depletion mode operation you can operate. And when VGS is negative, then this direction, left side, so here current is increasing. So this is your enhancement mode, and this is your depletion mode operation. Structure, we have to take substrate as N type, then channel source, then channel P type, then other parameters are remain same, or structure is remain same, only voltage polarity will differ. Now like transistor, JFET, here is also symbol. So instead of this, we can use this symbol, because when you make the circuit diagram, if you draw the structure, it is more complicated and it will take more space. So symbol we should use. So for N channel, these two, this is 1, this is 2. So what is the difference here? Substrate and source, both the terminals are here, and substrate is arrow marked. And then the second one, source and substrate are sorted. So we can use as 3-terminal device. This is 4-terminal device, this is 3-terminal device. For you, it is more important if you take, because 3-terminal device you are using and we are sorting the source and substrate. So this will be more prominently used. And another thing you can mark, like NPN, PNP transistor, whatever assumption we have taken, whatever arrow mark concept, here it is little bit different, just opposite of that. For NPN transistor, arrow is outgoing, means that is N type or NPN type. Here arrow is incoming, means that is N channel. Similarly for P channel, arrow is outgoing. That concept you should remember so that you can easily remember the symbol. Now we'll move to the other type of MOSFET, enhancement type MOSFET. So here also the depletion type MOSFET, enhancement type, everything is remains same. Can you just tell me what is the difference in the structure? See the structure clear, means more focus on structure, and tell me what is the difference. What do you observe? Do you find any difference in the structure? No. That means you are not listening properly. Okay, now just I am showing that previous one. Let's see how many of you will tell. See the structure, this structure. This is the structure. And now whatever I have drawn, the opposite one here. What is the difference?
सर पहले वाले में बीच में एक एन चैनल है.
Yes, very good. So that is the difference. Depletion type, the existing channel is present, but enhancement type, channel is absent. So what is the role of channel? Suppose the electron is present here. In this case, electron will find more number of electrons because this is N-type material. Okay, here also electrons are present. But between these two N-type material, P-type material is there where lot of holes are present. Now, if the electron, even if I am applying some positive voltage here, when this electron will come to P-type substrate, then it will recombine with these holes, so they cannot reach to drain side. So the movement of carrier from source to drain is not possible here if channel is not present. Yes or no? Like there is a river flowing, okay, and you are here. Now, if you try to move this side without any boat or breeze or anything, any medium, then definitely you will flown away. So here also same thing. This side electrons are present. This side electrons is present, but they cannot move from this side to this side because in between pool of holes are present. Okay. So what I'll do so that I can create the channel, or you tell me what is the solution so that even if the channel is not present, the electrons will move from source to drain. What I'll do? How to create the channel? Or you tell me you are present this side of the river and you want to go to other side. What you will do? There is no bridge, there is no boat, you don't know swimming. Okay, so how will move from here to there, that side? Obviously you have to make a bridge. Yes or no? You have to make a bridge so that you can walk through this side to that side, and the bridge strength should be sufficient so that your weight can be sustained by this bridge. So same concept will apply here. Here more number of holes are present across the channel region. Now what voltage across the gate I'll apply so that the holes will be repelled back and electrons will be attracted and build the channel? Tell me, positive voltage or negative voltage I'll apply across the gate so that whatever holes are present here, they will be repelled back and electrons which are present as minority carrier in the p type, they will be attracted here and build the channel.
Sir, positive.
I must connect a positive voltage so that holes will be repelled back and electrons will be attracted toward the channel, and the voltage even just I connect 0.1, 0.2 volt like positive, then it is not sufficient because the strength of the channel should be sustainable, the flow of carrier. Okay, so the minimum voltage, the minimum positive voltage I should apply so that the electrons will accumulate here, lot of sufficient electrons will accumulate here, and the electron movement from source to drain will start, is called as threshold voltage of E MOSFET. Okay, depend upon doping and all, the value may vary. So maybe 1 volt, 2 volt, 1.5 volt, 2 volt, anything. So the minimum voltage I should apply here so that the channel will create and current starts flowing, is called as threshold voltage. Is it clear? So the difference you can see here, there is no channel, it is written here, and when I apply positive voltage, see, you see this figure, see here what I have written, VGS equals to VT equals to plus 2 volt, and you see the current is very near to the x-axis. That means it is increased, not zero, but very small current. That means I can say when I apply 2 volt across the gate terminal, then channel is created and current starts flowing, but it is very less. Okay. Now when I connect 3 volt, 4 volt, 5 volt, 6 volt, 7 volt, 8 volt, then more and more electrons will be attracted towards the channel. Channel electrons will increase and current starts increasing. And overall trend, like previous case, here also the same trend will see. How? When I connect VDS, positive voltage, like this, you see here, this is my N-type material. So N-type is connected to positive and P is connected to less potential. So here the junction is reverse biased. Okay, here also the junction is reverse biased. So current initially increase, then it will block the channel, penetrate into the channel, then saturate, pinch off voltage, then the characteristic whatever we have received or we have got in the depletion type MOSFET, same type of characteristic will get. But only difference is that here current will increase. When I apply positive voltage more and more, the current will increase. So initially current will increase, then saturation or pinch off point occurs, then it will saturate. Okay. Now if you observe the trend here, when I apply more and more positive voltage, current is in increasing trend. It is not decreasing. Can I give negative voltage here? Anyone? If I apply negative voltage here, can I get any channel?
No, sir, no channel will be there.
Because already p-type material is there, and if you apply negative voltage, more holes will accumulate. So that will not help to build the channel. So we cannot apply negative voltage here. Okay, only positive voltage we can apply. So current will increase. Now, if you draw the transfer characteristic, so this is your VGS. So for VGS 0, current is 0, plus 1, channel is still not built up, then plus 2, just the channel is built up, that is threshold voltage. And after that, the current will increase. As I increase the current voltage, the current will increase. Okay, this is hypothetical, means VT 2 volt here it is, for example, it is given, it may vary. So current is always increasing trend. So it is a enhancement mode type of operation. Okay, so you just remember for depletion type, it is decreasing, increasing, or depletion mode, enhancement, both can be operated, but enhancement type means it is only increasing. Okay, VGS positive, the current will increase. And the equation is little bit different here. You see the equation, ID equals to K into VGS minus VT whole square. This is non-linear graph. You see here, this is non-linear graph. So K into VGS minus VT whole square, where K is a constant. It will be given in the question if it is coming. Otherwise, this ID on divided by IG on minus VT whole square, these values will be given, and you have to find K and put it here. Okay, so that will give you at any point, depend upon the input voltage, you can find output current. So from here or this equation also evident that input voltage variation will affect my output current. So this is your voltage control device or FET. Now you see the P channel. If you consider the P channel, VT will be negative, just opposite of that. Okay. And when you increase more and more negative voltage, more and more current will increase, and transfer characteristic in the left side of the axis, because VGS is negative. And symbol wise, any difference to mark here? Previous symbol and this symbol? Not remember the previous symbol. Let me show that one. See this one. This symbol and this symbol. Any difference? Do you mark?
Yes, sir.
Here the gaps.
Yes, sir, the gap, sir.
The lines are broken. So it indicates the channel, pre-existing channel is not there. Okay, you have to build the channel, then only the current can be flown across the transistor. Okay, so I have already uploaded this material in the classroom. You can go through that. And next class, that means Monday, we'll see one application of this one, and advantages of this MOSFET and application of this one. And one little portion I have skipped in the JFET, parameter of JFET, that I'll discuss. Then we'll go for the test. Okay, weekly test I told you. So due to shortage of time today, it is not possible. So Monday we'll take the test as well as this portion will complete.
Yes,
Okay,
sir.
sir. Sir, test up till this MOSFET now. Today what I
JFET. MOSFET we'll discuss later on.
Okay, sir.
Only transfer means ट्रांजिस्टर कैरेक्टरिस्टिक्स से लेके जेफेट तक. ठीक है, नेक्स्ट वाले टेस्ट में मॉसफेट और कुछ ऐड करेंगे एक्स्ट्रा.
तो MOSFET मतलब ज्यादा पड़ेगा और जो एक्स्ट्रा पढ़ाया जाएगा वो अलग है.
हाँ, वो नेक्स्ट में. अभी जेफेट और ट्रांजिस्टर कैरेक्टरिस्टिक जो प्रीवियसली हुआ था वहां तक. थोड़ा वेट करो, मैं अटेंडेंस ले जाता हूँ.